in the deep universe, there are worlds where the weather actively defies logic. Take HD 189733b, where hurricane-force winds whip molten glass sideways, or WASP 76b, where the temperatures are so extreme that iron condenses in the sky and falls as rain. We aren't guessing about these conditions. Modern observatories allow us to literally sample alien atmospheres from billions of miles away, detecting specific molecules like water vapor and carbon dioxide. Since the first deep space surveys, we have officially confirmed over 5,600 exoplanets hiding in the darkness between the stars. Our ability to see these distant worlds in such sharp detail creates a very persuasive illusion. Because we can map their skies and measure their temperatures, they feel within our reach. This is especially true for Proxima b. Discovered by telescopes stationed right here on Earth, it is a rocky planet orbiting the star closest to our own sun, sitting just 4.24 light-years away. Even more tempting, it lies entirely within its star's habitable zone. The surface temperatures are cool enough that liquid oceans could pool against its rocks, supporting a stable atmosphere. We know exactly where it is. We have calculated its mass, tracked its orbit, and isolated its position in the sky with perfect precision. We are capable of mapping the oceans and analyzing the weather of worlds trillions of miles away, yet we remain physically locked within our own solar system. A massive, invisible wall stands between what we can see and where we can go. The answer starts with the laws of physics. Looking at this energy curve from Einstein's special theory of relativity, you can see the trap. To accelerate an object with mass to the speed of light, the energy required shoots toward infinity. It is a hard limit built into the fabric of reality. That physical cage makes seemingly small distances utterly lethal. 4.24 light-years translates to a physical gap stretching past 40 trillion kilometers. To cross that gap using the fastest spacecraft humanity has ever built, it would take a staggering 80,000 years. To put that timeline in perspective, if a group of Neanderthals had launched that probe while roaming Pleistocene Europe, it would only just be arriving in the Proxima system today. The combination of vast distance and the absolute speed limit of the universe guarantees that traditional physical travel to our closest stellar neighbor is impossible within the lifespan of any civilization we know. Scientists have proposed workarounds. The Breakthrough Starshot project envisions using arrays of ground-based lasers to blast tiny sails up to 20% the speed of light. But solving propulsion only reveals a much deadlier problem. Interstellar space is filled with microscopic dust. At a fifth of the speed of light, a single speck hitting a probe carries the kinetic force of a small nuclear bomb. Then there is the targeting. If the launch angle deviates by even 1,000th of a degree, that tiny error compounds over light years, sending the craft billions of miles wide of the target. And even if a sail survives the dust and threads the needle, it has no fuel to stop. It would screen past Proxima b in a fraction of a second, unable to enter orbit. Between the sheer kinetic violence of the interstellar void and the impossible math of precision targeting over light years, any physical journey to the stars effectively becomes a suicide mission. The destination itself is just as unforgiving. Proxima Centauri is a highly volatile red dwarf star. It regularly scorches its planets with massive X-ray flares, violently stripping away any atmosphere or water that might gather on the surface. If we tried to send humans instead of probes, we'd need massive generation ships. This creates a moral and governance challenge with no historical parallel, forcing future descendants to live out their entire lives isolated inside a cold, drifting steel vessel. Human biology is tuned to the rhythm of Earth's 80-year cycles. We have no biological or psychological framework for existence spanning the millennia required for interstellar travel. Sustaining a functioning society inside a lightless, drifting hull for dozens of generations is a nearly impossible task. Without a connection to Earth's biosphere, the social and mental structures that define us would likely erode long before the ship reached its destination. We are left caught between two boundaries. In our own solar backyard, Pluto represents the absolute physical edge of where we can realistically send our machines. Just beyond it, Proxima Centauri stands as the unreachable wall of physics. Through our telescopes, we possess near godlike visual knowledge of these distant systems. We can watch their weather, map their surfaces, and count their moons. Yet physically, we are entirely confined to our starting point. These distant points of light reflect our own limitations. They mark the boundary where human curiosity meets the hard reality of physical law, reminding us of exactly how much of the universe remains beyond our reach. The light we capture from these systems left its source years ago. We are documenting the history of worlds that, by the laws of physics, will remain visual data points rather than physical destinations. We spend billions dreaming of reaching other suns, yet we struggle to maintain the ecological balance of the only planet known to support us. Because human bodies are permanently quarantined by the laws of space and time, our survival cannot depend on fleeing to the stars. It relies entirely on preserving the fragile, incredibly rare world directly beneath our feet.